All right, so we're going to talk about the Chapter 4 review for the applications of integrals. This is the FRQ portion, question 1. It has 3 parts. We're going to talk about part A in this video and then move on to B and C in new videos. So for part A in this question, they've given us a table of water temperature in the bottom row here and time elapsed in the top row. So the water temperature is increasing as the time increases. Part A is asking us to use the data in the table to estimate W prime of 12 and then to explain our answer in the context of the problem and what it means. So the first thing we have to do is realize that this is asking for W prime of 12, whereas our original function is just W of t, not W prime. So we're not just looking for 12 and what number is it, we're actually, we need to find a derivative, right? So what we need to see here is that a derivative is the same thing as a rate of change, which means how is the temperature changing over time. And in order to find the derivative when we only have a table, what we need to do is essentially find the slope of the function at around t equals 12. So in order to find the most accurate slope at this point, we want to look at the x values that are closest to the one that it wants us to actually calculate for. And we can show why we need to do this if we do a very rough sketch of just a general curve on a set of axes here. So I have an x and y axis, and I've got a function like this. It doesn't really matter what it looks like. This isn't a representation of anything from the problem. It's just illustrating this point. So if I wanted to find the slope of this curve at a certain point, let's say right here, we'll call this C. If I wanted to find the slope of this curve at this point, since I have the graph, I can just go ahead and look, and I can see that the slope looks like it's going about like that, right? So it's going up this much for this far it goes over right at that point there. It's a very different slope from over here, for example. This is going downhill. Here in the middle, the slope is 0. So this has its own distinctive slope at this point. So if I only have a table of values, I can find the slope by doing rise over run. But the closer that my values are to this x value, the closer my slope is to the one that I'm actually looking for. For example, if I choose x values that are very far away from C, so instead of being right on C, if I choose this value here and call it A, and this value here and call it B, since they're so far away, the slope between these 2 points, between this point and this point, actually goes something like this, which, although it's still going uphill, is much less steep than the slope I'm actually looking for. And the closer and closer my x values get to the point that I'm looking for, the more and more the slope between the two lines matches the slope at this value C. Which is why we need to pick x values, or in this case t values, that are as close as possible to the value we're actually trying to find the slope for, so that we can get the most accurate estimate for what that slope is. So if we take a look at what we've been given here, they want us to find the slope at 12. And here we have 9 and 15, and 12 would be somewhere in the middle. So we're going to go ahead and choose the values 9 and 15 to help us calculate the slope between them, because it'll be a good estimate of what the slope is at the point between them. So in order to calculate slope, we use a function that should be familiar. It's the function for the rate of change or the slope or the derivative. We've seen it over and over again in a variety of ways. So the slope in general is f prime of x is going to be f of b minus f of a over b minus a. And this should be familiar because b and a, these are x values. So this is the change in x. This triangle here is the symbol for delta, which is a Greek letter that just means change. So this is the change in x values. And if we take x and plug them into our function, we get out y values. So on top, we've got our y values that we're subtracting. We have the change in y values. This should look familiar because the change in y values, which is the height of our graph, the vertical axis, this is our rise. And the change in x values, this is our horizontal axis here, that's the change in run. So if we calculate the change in y over the change in run, we found the rise over run. That's our slope, which is what we're trying to find. We're trying to find f prime, right? So in this particular case, we're trying to find w prime. So we're going to do the exact same formula as we just did here. We're going to find the slope, which is the derivative. They mean the exact same thing, except we're going to do it with the function that we've been given. So instead of f of x, we've been given a function called w, and instead of x, we've got a t variable. So we've got w prime of t that we're finding. Now, in particular, we're trying to find w prime of 12. So not just any t, we want 12 specifically. So we're going to go ahead and use 12 here, but it won't change the math that we do because we already talked about how to find the values as close to 12 as we can get. So we still need w of 15. We need to use 15 and w of 9 because they're the two closest x values here to the number that we're actually looking for. And then we're going to do 15 minus 9 on the bottom. Now be very careful when you're writing your w of 15 and your w of 9 because 15 is the t value that we plug into our function. It's not the same number that we get out. We don't want to write w of this number that we got out because this isn't a t value. This is actually the height of our graph. This is a temperature. This is degrees Fahrenheit, not time. So we don't want to plug in degrees Fahrenheit where we should be plugging in time. So w of time is w of 15. But we can rewrite this with what we know this value is. So after 15 minutes, we know that the temperature is 67.9 degrees. So we can say 67.9 for that one. And then w of 9 is plug in 9. We get out 61.8 minus 61.8. And then we're going to divide that by 15 minus 9, which we can calculate to be the number 6. That's fine. Because this is an FRQ, this is where we can stop with our math. We don't have to simplify anymore. You can if you want to, but the more you simplify, the more opportunities to make a mistake and lose points, whereas this will get you full credit. Now, if you did go ahead and subtract this, we could see the difference between 67.9 and 61.8 is actually 6.1 over 6, and you are allowed a calculator on this portion of the test, so you can plug this in and actually get a decimal out that's more accurate. That's fine, but this is an okay place to stop as well. You don't have to keep going any further than this. So the second part of this question is asking us to interpret the meaning of our answer in the context of this problem. So what we've just found is the slope. We know that. But we also know that the slope and the derivative mean the exact same thing as the rate of change. So what we found is between 9 and 15, our temperature is changing about 6.1 degrees every 6 minutes. So this is the difference in our temperature. So this is degrees Fahrenheit. And down here, this is the difference in our time. So this is measured in time. This is minutes. So our units are actually degrees Fahrenheit per minutes, which is why it's a rate of change. Rate of change is always some sort of measurement divided by some aspect of time. So our original measurement is something we can take recordings of on our own. So it's length or it's mass or something like that, volume, or in this case, temperature, something that we can record. And in order to turn it into a rate, we have to divide it by a unit of time. So miles per hour is the most common one. So miles is our measurement. Miles per hour is our rate. And then if we take the derivative again, we end up with looking at how the miles per hour change over time. So how your speed changes over time, that's what acceleration is talking about. So in this case, we started with a position function, which is just a measurement of numbers. And then we took a derivative, which is how we ended up with our rate. So because we're talking about our rate of change, we have to be specific when we talk about this. So this is a measurement of the rate of change of something, which is going to be of the temperature, right? So this is the rate of change of the temperature. But because, and this is something that they didn't specify in the test, but when a question asks you to explain the context of a formula before it has asked you to actually solve the formula, which is something that we did on the review question from before or in the in the future, we might be asked to explain a formula before we solve it. If that's the case, then you can be very general with your description. But if they ask you to solve the formula before they ask you to explain it, you have to explain your answer as thoroughly as possible. So we don't want to just call this number a rate of change, because change is very vague. How did it change? Did it go up? Did it go down? Did it go backward? Did it disappear? You know what I mean? So we want to describe how this changed. So this is the rate, this word is very important, rate of increase. It changed positively. This is a positive 6.1, so increase. If this was a negative number, then it would be the rate of decrease in temperature, but we're talking about increase in temperature. In temperature, the rate of increase in temperature in degrees Fahrenheit per minute, of the water in the tub. Now we're almost finished. We've talked about the rate. We mentioned increase. And because the question is asking about temperature of water, we mentioned the temperature of our water. We mentioned our units. That was important. It said mention units in the question. So we had to make sure to do that. It says it here using units. There's only one thing that we've left out, and it's part of the original question. It says use the data in the table to estimate W prime, which is the rate, of 12. This number 12 is going to be really important in our answer as well. So this is the rate of increase in the temperature in degrees Fahrenheit per minute of the water in the tub at 12 minutes. So we can't just say, in general, the rate of increase in the temperature. We have to say this is the specific rate of temperature increase at 12 minutes, because the rate of increase is going to differ, just like the slope of a curve will differ depending on what x value you're looking at. The rate of increase in this temperature will differ depending on which x value, which time value you're looking at. So we have to be specific. Now, it doesn't have to be written just like this. You can rephrase it if something is more comfortable for you, but the main points that you have to mention are that this is a rate, it's increasing, it's the temperature of the water, it's at 12 minutes, and it's measured in degrees Fahrenheit per minute. Okay? So that was part A. We're going to go ahead and move on to part B.